Hi guys, welcome back to UGC lecture series on lasers and their applications under Swayam portal. Now we are going to see another major measurement, major applications of laser, that is based on Michelson interferometer. This particular instrument called Michelson interferometer is the first one to win Nobel Prize for an American. Not only that, that particular measurement done by Michelson is the one which changed the history of physics. How? Let me explain. Go back to the picture. I will show you. What you see at the bottom is a typical Michelson interferometer instrument. Most of you in undergraduate lab, wherever you have BSc physics, you will have this instrument. What it starts, now I have put laser. You put a laser, it will come out as a linear straight line beam of about 3 millimeter or 4 millimeter. Then put a lens, put another lens. Look at the diagram. If the focal length of these two lenses, focal point, coincide, if for example, if the first lens, small lens, has a focal length of 5 centimeter, another lens, the bigger lens, imagine that has a focal length of 10 centimeter, then what would happen is, all that you need to do is adjust the distance between the two lenses such that the focal point of this lens and this lens just coincide. Then what would happen is, since the angle theta is same, then if the beam on the left side, that the one that comes out is 3 millimeter, which falls on the small lens, what comes out from the bigger lens will be 2 times the size. It will be 6 millimeter diameter. So you will have a bigger beam with a parallel waveform. That is what you mean by spatial filtering, or this is called beam expansion. Beam expansion means, watch out, if I have a laser beam, if I put a lens, the lens will focus it and then it will expand. The beam will keep on expanding. That is not beam expansion. Scientifically, beam expansion means the laser that comes, the light that comes out from the laser as a parallel wavefront. So if you want to have a bigger diameter beam with a parallel wavefront, this is the technique we employ. What it means is, what comes out from a diode laser is a beam of, let us say, 3 millimeter diameter. I put a lens of focal length 5 centimeter. I put another lens of 10 centimeter. Then adjust this distance such that this focal point and this focal point coincide. Then if this coming beam is 3 millimeter, what comes out will be a parallel wavefront of 6 millimeter, because the focal length differ by 2. Automatically, the diameter of the two beams also should be differing by 2. That is all. This is what we got, proper beam expansion. Why do we want this one? For the Michelson interferometer, we want a parallel wavefront of typically 6 millimeter diameter. That is why we say all this one. Then you put a 50% mirror, which is called the beam splitter, which will split the beam into 2 equal quantity. Then one beam will travel along y axis, another will travel along x axis. Then on the y axis you put 100% reflecting mirror. So the light goes and comes back. Next one, here you have another mirror. In the olden days, people used to have another mirror. Now, because of the multiple reflection by this mirror and this mirror, it will lead to a lot of confusion. So, what we do now is you put a recto reflecting prism, then the beam will come back. It will come back parallel, but without any change anything. So, you must allow it to come back. You need certain type of tilting everything. So, the beam comes back. Then next step, you adjust this distance and this distance so that they travel equal distance. If they travel equal distance, then the light which went up in the y axis, the light which went along x axis, both will come back, meet at the beam splitter and travel along the same direction and go to the detector which is at the bottom. If the two distances are exactly same, you will have a bright fringe on this one. This is the beginning. This is the very precision instrument to measure any path difference between the two beams introduced by some reason or another, and this is very precise. This particular experiment, as I told you, played a very vital role because it is this experiment which showed that light traveling in this direction, light traveling in this direction, both have the same speed, which was not acceptable at that time because the whole instrument is traveling, let us say, along the x axis somewhere, but in upside it is not traveling, it is always moving only in this direction. The light which left this side is being carried by the earth, the light which went upside is not so. So, there should be a path difference, but experimentally it was found that it is not showing any difference. That means light, whether it travels in y direction or x direction, will have the same speed. The earlier concept was there is some kind of medium which is called ether, and the light is supposed to travel with ether as a frame of reference. Now, once this experiment has been done and proved nullified, what do you mean by nullified? Means the light whether travels in x axis or y axis, it has the same speed. That means ether is not there, or at least ether could not be detected. So, there was so much controversy. So, people started working their idea of ether or light traveling on ether as a medium. Now, why ether came into the picture, I should explain. All the time before 1900, we are all familiar with so many types of waves. The most common wave is a wave on the water in the seafront. If you go to any beach, you will see the waves coming one after another. Waves are coming one after another, but remember, the wave is going up and down, but the medium is here. The medium is water. The wave is going up and down like this one. This is what happens in the seafront. In fact, if you look at carefully, next time you can do this experiment, make sure that somebody is holding your hand, don't go to near the sea. Throw a floating object like a bottle, a plastic bottle for example, or any other bottle. Don't throw plastic on the water. You take a wooden piece, yes, just take a wooden piece, throw it into the sea as much as you can see. Then what you will see, the wooden piece will be going up and down, even though the wave will be going like this one. The wave will be coming to you, towards you and going away. Wave will be coming towards you and going away. It travels in this direction, but remember, the wooden piece will be traveling up and down. This is a typical example for a transverse wave. classic example for a transverse wave. Light is a transverse wave. So, there should be a medium. For sea you have water, here where is a medium? Ether is supposed to be the medium. So, up to that everything was fine. This was acceptable even to a giant thinker like Maxwell, and we went on, all the scientists went on work on this one. Things were all going very well up to 1905. In 1905, Einstein came in and he said, in one stroke he brushed away the existence of ether. He said, since ether could not be detected, let us assume, or let us not bother about ether, let us just forget it. Let us try to interpret the same result without bringing in undetectable ether, as simple as that. Then he said, light is not traveling with ether as a frame of reference, it is traveling by itself. So, light in any direction will have the same speed. That is the first step of theory of relativity, and after that he went on to so many other things. I will not go into the details of theory of relativity. All that I am trying to bring back to your memory or bring back to your attention is this one particular experiment, Michelson interferometer experiment, has been so important that theory of relativity came into the picture. Once the theory of relativity came into the picture, which was not accepted for 10 or 15 years, remember. From the theory of relativity, Einstein was led to show that E is equal to mc square. Even then people did not believe it. So, the theory of relativity came in 1905 and he took Nobel Prize after a long time, not for theory of relativity, because people were not able to believe what he says is correct, but they realized that he is a genius, but they do not want to commit theory of relativity. So, as a compromise, he was given a Nobel Prize for photoelectric effect. All the story is very famous historical even. What is important for me or for you and me for the time being is, this Michelson interferometer was the one which proved special theory of relativity. Okay? Now, let us go. Let us make a big jump. That was the story in 1915. So, let us say 1915, or I would even say 1920 for example. Next story, next part of the story, that is the first part of the story. The second part of the story is something like this one. Einstein proposed special theory of relativity. After few years, he proposed general theory of relativity, which were far more complex than the special theory of relativity. In general theory of relativity, he said, I mean, it's a long mathematical calculation which I never understood. All that I know, the final equation, final result is, the gravitation is not an attraction between two masses. This is shocking to Newton. If he was allowed, he would have got very angry also. According to Newton, gravitation is a property of mass. What we mean by property is, anything which has a mass will attract another object which has a mass. Any object should have mass. For example, look, I am standing here. Opposite you have a camera that has a mass. I have a mass. I am being attracted by this and I am attracting this. We have a gravitational attraction between the two just because both have mass. This is the theory of gravitation. Now, we will not go into the detail anymore. Einstein said, this kind of gravitation, which is not a property of mass, it is a property of space-time curvature. It is a property of the changes introduced by me on the space-time curvature. I am in a space. I make a certain change in the curvature, and because of this one only, if I throw a coin, the coin will fall down. That is his theory. So, gravitation was converted into a space time changes. That is all what he said, and then there are so many other theories. This new idea about general theory of relativity went to, I mean, there were so many scientists who kept on expanding, improving, and finally they said in the galaxy, remember, from America, from Europe, from India, you jump into the space, go to the galaxy. Galaxy means far, far beyond moon, sun, everywhere. Just keep going. At a very long distance, there are heavy masses like black holes. Black holes are extremely dense masses. They are heavier than the sun that with which we are all familiar. They are heavier than all the planets, all the big stars that we are all familiar. Now, the interesting point is, at this point I must bring to an important sideline story. Chandrasekhar, who was at that time, he was a student in President's College, he was aware of the theoretical changes, I mean the great upheaval going in physics. He was very conscious, he was aware of all this one. So, he wanted to work on this one. So, he understood general theory of relativity. So, he started working on it. Then, based on his initial few papers, he was able to go to UK. He went there and he started working with him. And then, what is important is one, at the age of 30 or 40, he predicted that sun is a star and there are hundreds and thousands and millions of stars in the galaxy, and there are few stars which are not bright like a sun, but they are very, very dark stars. Why say are dark? They are so dark that the gravitation pulls even the light not to come out. Since the light is not coming out from the heavy star, even light cannot escape. This is called the black hole. He predicted that black hole has certain heavy mass. Sun is a very bright star and there are so many stars in between. There are some stars which will be yellow, some stars will be red, some stars will be white, and some stars will be very big, some of them will be so small. So, it is like if you go to any jungle, go to any Kerala forest, you will have long, very big teak tree and there will be small tea tree also. Both will be there, tea tree, not a teak tree. Tea tree is so small, you can just pluck it. Teak tree, you will be looking at it so high. So, like that, there are hundreds and thousands of stars of different masses, different sizes. The point is this one. A black hole, one black hole, another black hole, if they come together, they are like two giants. They would start attracting each other because anything having a mass should attract. When they just come together, if they merge together, they will fuse like two mercury droplets. If they merge together, they will produce a big change in the space-time curvature. That means they will produce gravitation wave. Let me explain again. Imagine two elephants. Take example, two elephants. They were all friends for a long time. Imagine these two elephants meet after a long time. They come and go close together, hug each other. There will be a big noise when they come together. When two elephants come together, hug together. In a similar fashion, when two black holes come together, they will produce a dramatic change in the space time continuum. That change in the space time continuum will produce gravitational wave. The gravitational wave for a particular typical example of two heavy black holes coming together, two spherical one coming to the fusing together, will form a spherical, not a spherical one. It will become like a dumbbell. Imagine, let me put again. Imagine two, if you are familiar, you can easily do this experiment. Take any leaf, bring two droplets, early morning droplets, just bring them close. When you push them together, you will see two spherical droplets fuse together to become a cylindrical dumbbell like shape. This is all what would happen when two heavy black holes come together. Now, when this happens, there will be a gravitational wave which will be not spherical, it will be cylindrical. Now, look at it. Can we ever detect this one cylindrical wave? Yes, if we could detect such a cylindrical wave starting from in the galaxy few thousand miles away, they will travel as a cylindrical gravitational wave. Imagine that they come to India or USA or Europe, anywhere. Then this is where Michael's come into this picture and laser come into the picture. Let us build a laser based Michelson interferometer in USA, in Europe, 3 or 4 places. Now, keep on observing, keep on waiting for such a big event in the galaxy. When this happens, there will be a cylindrical type gravitation wave coming and reaching more or less with the same certain small time difference. First it will reach Europe, then it will reach America, because you see there is a big difference. It will reach, then it will pull. Remember, go back to the Michelson. This side of the mirror will be pushed like this one. Then you can find the shift in the fringes that you could be measuring using a photo detector. If you could find out the number of fringes that has happened due to this gravitation wave, number of shift in the fringes due to gravitation wave, if that is same as you measure in Europe and that you measure in America, if the number is same and if they come after time difference, then that could happen only due to the expected or predicted gravitation wave that was predicted long ago by our Einstein and Chandrasekhar, so many scientists were all astrophysicists, cosmologists. This was what is expected, then this was predicted. European government, American government, including Indian government, they all did what they call crowdfunding. I will give you $1 million, you give some $10 million, like that. They all put their money. Then what happened? All these put together, they built the instrument. Eventually, in 2020, they were able to really verify whatever Einstein predicted. Then, for the detection and confirmation of gravitation theory, a set of scientists were given a Nobel Prize. What I am trying to bring back to recollect is this was possible. I repeat, this was possible only because a frequency stabilized laser. Until the laser came in, they were not able to even think of such a possibility. They thought about it, worked on it, and eventually they were able to show that whole idea predicted by Einstein, designed by the scientists, worked together. This is something the whole mankind should be proud of this one, and that is a property of this experiment. Now, let us go to another very important application. The same Yeah, I am just showing a typical modern laser interferometer. Whatever I said, I have just explained. I can show it again. You start with the laser. There is a beam splitter. One part of the beam goes to the retroreflector. It just goes here and comes back, and then you have another mirror. Then both of them come together, produce interference pattern. If initially all these adjustments are adjusted, you can make the distance in y axis and x axis same, then you will have certain reading. Then you pull it for small distance of lambda by 2. If you pull it by a distance of lambda by 2, the light has to travel additional distance of lambda by 2, another lambda by 2. So, the total path difference between the light that goes this side and this side will be lambda. So, you will have a new fringe coming up from the interference pattern. You can count, you see there is amplifier, digital counter, all these things are electronically arranged one. Eventually, it will show a very precise change in the distance between the two directions. That is all what it means. Now, this is the very great advancement of what was there when people use a sodium lamp. This is a standard instrument. See, this kind of instruments are available in many parts of the world now. Now, let us go to the next important. What I said is one very big advantage example of Michelson interferometer. This has certain important advantage in measuring the stress on the dam. See, what we mean by this one is, you see you have a big heavy dam which holds a lot of water. You have, I mean, you know HDG, you must have heard about HDG. Water will give a pressure not only in the depth, not in every direction also. Then the pressure given by water on the concrete structure will be very, very small. Such a differences can be easily measured using this kind of Michelson interferometer, as I showed you all this one. My point is this: you measure the dam stress using laser Michelson interferometer, which is commonly done in ordinary engineers nowadays. The gravitation is a very high-fi, world celebrated experiment. Between the two extremes, the same idea, same kind of laser technology are being used. That shows the versatility of this laser based small distance measurement technique. Thank you very much.